Okay, so previously we used Euler's method to approximate a solution to a differential equation. What we want to do now is find a way to adjust that to make it, a better approximation. So this is called the improved Euler's method. Remember, Euler's method said that we started with the point x naught, y naught, and we used the function. We had that the slope y prime was equal to some function f of xy. Okay, so this gave us the slope of the tangent line. Okay, so we used that slope at the point x naught, y naught to get this tangent line, and then we looked at the next x value, which was some distance h away from the initial point, and we used this formula to find the y value on the tangent line for that x. So we found that the y1 was equal to the previous y value plus the slope. So we found the slope at the previous point times that h value. Okay, and that was just using the tangent line. That's just the equation of the tangent line passing through the point x naught, y naught with the slope f of xy. Okay, so that's how we got that. And then you can see for this particular curve that that y value is not that great of an approximation. So what we want to do is find a way to adjust it and correct it before we just use that for the y value for the approximation for that curve. So what we're going to do is not just use that. We're going to first calculate what that y value would be using the tangent line. So now we have this point x1 y star at x1, so y1 star. So that's going to be that initial point on that tangent line. But what we're going to do, instead of using that for the y, we're now going to make an adjustment to finding the y by looking at the slope at that new point. So if we could find the slope at this point right here, by plugging it into this equation, we're going to get some new slope. So let's say that this was the slope determined by that differential equation at the point x1, y1 star. Well, you can see that's different from the initial slope of that tangent line that we used to get it. So what if we average those two slopes? So instead of saying that this is the slope or that this is the slope, we're going to take the average of the two. So what this value is here is the average of those two slopes. We're taking the slope at that initial point, which was the f of xn, yn, and then we're going to get the slope at that new point, which is the f of xn plus 1, y star n plus 1, average it, divide by 2, and then we're going to multiply by the h and add the y, and we're back to using this formula. All we're doing is we're adjusting what we're using for that slope by averaging two slopes, the slope at the initial point and what the slope of that projected point would be, and using that as the slope that we're going to use then from this initial point. And then once we use that slope, which is the average slope of those two, we're going to get the point on that tangent line at this x value. And you can see in this picture that that y value, which is the y value on that tangent, that new tangent line, is a much closer approximation to the y value on that curve at that point. So that's the idea behind the improved Euler's method. You're using what's called a predictor-corrector method. So you're predicting it using Euler's method, and then you're correcting it using the new information, the slope at that new point, combined with the slope at the previous point. So let's see what that might look like. Okay, so I want to use improved Euler's method to get an approximation for y of 1.5. So we're going to let the x equal to 1.5. That's what we're trying to calculate. And our initial value has x equal 1, the y is 1. So this is our differential equation. So this is going to give me the slope of the tangent lines at each point. So what I want to do is build a little table. I'm going to look at the x value, and we're starting at 1. We're going to look at a predicted value each time, and then we're going to get what the real value is going to be by using the corrector. Okay, so we know that for the first point that the y value is 1. So now the next x, we're going to use x equal 1.1. We're going to use a step size of 0.1 as they indicate up here. Okay, and then we'll go to 1.2. I'll go through pretty quickly because this isn't just kind of tedious to go through all this. So first, use Euler's method to find the y value at the point x equal 1.1 using the initial point 1, 1. So we know that we have this formula for Euler's method. So we'll do this. We'll say this is n and this one's n minus 1. Okay, and that'll be times 0.1 each time. Okay, so using that formula, our y1 predicted value will be the previous y, which is 1, plus the slope. Now I'm just going to use this 2xy. It's 2 times the previous points x and y, which is 1 and 1. Okay, and then times our h, which is the 0.1. So again, this is our slope calculated from this. Okay, so that's going to be 1.2. That's our predicted value. We're not going to use that. We're going to now find the average of the two slopes. So we're going to now use this formula. So this is for the star. Plus, we're going to look at the f of xn, yn star, and then times our h. Okay, so let's go back to here. So then our y1 will actually be the previous y, and now we're going to look at two slopes. We're going to look at the slope at the original point 1, 1, and now we're going to look at the slope at the projected point 1.1, 1.2, and each time I'm using this formula for the slope. Okay, so when you find that value, it comes out to be 1.232. Okay, so that's what we'll actually use for the y value. So now we can ignore this y star for that point. Okay, now we're going to y2 star. Use the previous point. There's the y value. I need the slope at that point. That gives me the slope times the h. Okay, that gives me 1.50304. And we're just going to use that to get the real y, or not the real one, the estimated y value. So now our y2 will be, again, the previous y, and now take the two slopes, 2, 1.1, 1.232, plus 2 times 1.2, 1.50304, that's the estimated value, divided by 2, and then times the 0.1. And that comes out to be 1.5479. So now that's what we're going to use, and we're going to ignore this one. Now the y3 star. Use the previous y value, the slope at that point, using Euler's method here to get the predicted value. Whoops, not dividing. And then times the 0.1, and that comes out to be the 1.9194. Now we're going to use the adjusted value. So again, the previous value, average the two slopes, now we're going to use the 0.13 and 1.9194 times the 0.1, and that comes out to be 1.9832. Okay, now predict the fourth one using just Euler's method. the slope. And here's our h value. That comes out to be 2.4988. Okay, now use that to adjust previous value. Let's average the two slopes. .4, and then the projected y value. Oops, 88 times the 0.1, and that comes out to be 2.5908. Last one, y5 star, previous y value, plus the slope, times the h. We get 3.3162. Okay, and now our y5, which will be the estimated y value for x equal 1.5. Two times the 1.5 and the estimated y value. And that one comes out to be 3.4509. Okay, so that's our estimated y at x equal 1.5. And if you look at the table over here, you'll see the values using the improved Eulers method. I just did the step size h equal 0.1. You could do it with a smaller step size and expect to get a greater accuracy. But here was the y values that we just predicted. This is the actual values. If you solve this, it is a separable equation, so you could solve that and get the exact equation now, get exact solution. And you can see that the error is very small. This is a 1% error to what the value was at x equal 1.5. So improved Eulers method, I don't have the values here for just Eulers method, but you saw them, we calculated them originally, and they were quite a bit off from the improved Eulers method. And there's other methods that use this same idea of averaging out those slopes. You could average the slopes of several points along the way if you wanted to, and we'll look at other methods that do that even do weighted averages, and you can set those to any way you want to weight them. So improved Eulers method, and then you'll have some homework and have another notebook to help you with that.